Hydrolysis comes from the Greek words hydro, for water, and lysis, to loosen or separate. What it signifies is a process that uses water to break apart and rearrange molecular bonds. Strong carbon-carbon bonds, or carbon-hydrogen bonds, aren't susceptible to hydrolysis. But if there's a weaker bond, and especially if the portion of the molecule that breaks apart is stable by itself in water, then there's a good chance that the molecule is susceptible to hydrolysis. You can first imagine this as the opposite of a condensation reaction. If a carboxylic acid and an amine or an ether can combine to form an amide or an ester bond, then the reverse process is also possible. Thankfully, the amide bonds in our proteins aren't susceptible to hydrolysis at body temperatures, or else we'd be in real trouble. The same is true for the bonds in nylon. If it were, then nylon would dissolve in water. However, under the right conditions of temperature, pH, and catalysis, both protein and nylon can break down into their constituent parts. After all, our digestive system does break down proteins, and acids can break down nylon. And the esters in fatty acids can be broken down into carboxylic acids and glycerol under basic conditions during the soap-making process. One professional area that we might apply hydrolysis is in the decontamination and destruction of chemical warfare agents. To understand why and when, first we need to consider the mechanism. Let's compare two different types of agents, both from the First World War. First, we'll look at phosgene, a choking agent. Looking at its structure, you should recognize it as like an aldehyde, similar to formaldehyde. We could even call it 1,1-dichloromethanol. Phosgene relies on hydrolysis for its mechanism of attack. When phosgene comes into contact with the water in a person's eyes, nose, or lungs, the water substitutes position with chlorine, generating 2 hydrochloric acid molecules for every phosgene molecule. Phosgene's action is relatively slow, taking up to 24 hours for its effects to be felt, allowing its victims to take in a stronger dose before they realize that they've been exposed to the gas. The hydrochloric acid released scars and damages lung tissue, affecting the victim's ability to breathe, hence the name choking agent. Hydrolysis, with higher heat and higher pH, is especially effective against phosgene because it emulates its own mechanism of action. In fact, it's so sensitive to hydrolysis that rainy or foggy weather can be enough to render phosgene completely ineffective. Far better for it to react with water outside the body than inside the body. Now let's compare that to sulfur mustard, a blister or vesicant agent. This is an oily liquid that can penetrate the skin and interrupt cellular processes. It also releases its chlorine, but instead of creating an acid, mustard's greatest harm comes from cross-linking strands of DNA or RNA. This causes cells to undergo necrosis or apoptosis, cell death, and creates large, painful blisters between layers of skin. Because it affects DNA, mustard can also have long-term healthcare effects, including cancer. Hydrolysis does not render mustard safe the way that it does for phosgene. If mustard comes into contact with water outside the body, it will still react, but instead of cross-linking DNA, it cross-links with itself to create a branching, networked polymer. Now I hear you saying, that's fine. If it bonds with itself, then it can't attack my DNA or enter my cells. And that's true for a thin layer. But what about an artillery shell that's been filled with sulfur mustard, dumped overboard, and sat on the sea floor for 70 years? If the metal is breached, then the surface of the mustard forms a polymer that protects and insulates the material inside. And if that shell is brought to the surface by a fishing trawler, and the polymerized outer layer is disturbed, then the pristine chemical weapon is there waiting, just as effective as the day it was manufactured. Of course, mustard can still be decontaminated using other methods, especially using strong bleach and heat, but hydrolysis alone isn't enough to guarantee that it's made safe. A thorough understanding of organic reactions is important to help commanders in the field make good decisions about the risks, the defense, and the decontamination of chemical warfare agents.